Welcome back everyone. In this lecture, I will talk about group acting on a set. Okay. So, this is very important actually notion and tool. Okay. So, this group action is actually you can see everywhere. So, for example, in topology, geometry as well as in combinatorics. Okay. So, mostly actually we will use this group action in order to prove many interesting results about group itself, okay, by using various action of group on itself. Okay. So, from the combinatorial point of view, when some group is acting on a set, okay, then that group possesses lots of symmetries. Using those symmetries, one can actually uh, understand the set, the underlying set in a better way. For example, from the combinatorial point of view, let us say we are interested in counting the number of elements in the in a given set. Okay. Suppose we can find a group that is naturally acting on that set, okay, and then that action is, let us say, transitive action and so on. So, then using this information and information about the groups, one will be able to count the number of elements in the set. Okay. So, I will demonstrate all these things using some examples. Okay. But before that, let us begin with notion of group action, and then let us get familiar with this idea. Okay. It is a very powerful idea. Okay. So, somewhat it uniformizes all the things that you have seen so far. So, let us begin. Okay. Let us fix some notation. So, as before, so we always say denote G by a group. Okay. So, what we are trying to understand? So, we want to say that this group is acting on a set. Okay. So, you may wonder like what is the motivation behind this. Okay. Let me start with one example. So, then it becomes clear what we are indeed talking about. So, let us take somewhat geometrical example. Okay. Let us take Rn, so which is n dimensional space. Okay. So, one can treat it as, okay, for example, we can take a standard inner product and then that will give you distance. So, this can be viewed as Euclidean space. Okay. So, now what one can do, one can look at all possible invertible maps from Rn to Rn. Okay. So, that is denoted by GL of Rn. So, this is the set of all invertible linear maps, okay, from Rn on to Rn. Okay. So, then this is a group. So, we can say that any element of this group is indeed acting on this Rn. Okay. So, that means given any element G in this GL of Rn, so you have a map, associated map from Rn to Rn. So, what it is? It is actually sending some vector to its image. Okay. That means this given element, okay, G in GL of Rn. So, it is acting on Rn as invertible linear map. Okay. So, because here I started with linear structure. So, we are actually taking this invertible linear maps and we are looking at the action that possess more properties. But from the purely set theoretic point of view, okay, if we want to understand the group, this group acting on this Rn, okay, then we may not know what is linear maps and so on. But without that, if you think about it, what this G indeed does? This G is simply a bijective map from Rn to Rn. Okay. The important thing is from purely set theoretic point of view, G is bijective map. Okay. So, this is the level of abstraction that we will actually look at it when we actually go to group action for the general group G acting on some set capital X. Okay. So, note that, so in this example itself, what is the meaning of this GL of Rn acting on Rn? So, that means given element G in GL of Rn, we have a natural map from Rn to Rn. Not only that, when you compose two maps in GL of Rn, that actually somewhat reflected here on the right side as well. Okay. So, let me just to make things somewhat more easy. So, let us denote the image, okay, as let us say some Tg. So, Tg is the linear map that we are associating with this G. Okay. So, G is like a matrix, okay, and given vector V you are associating GV. So, that is your map Tg of V. So, Tg of V is just given by G. So, now if you think about it, so you have G1, so that is mapped to Tg1, and then you have G2 which is mapped to Tg2. Okay. So, then we can compose these two maps on the left side. So, because this is all happening inside GL of Rn. Okay. So, then what you expect? You naturally expect when you look at the image of this Tg1, Tg2, so that should be just the product of Tg1, Tg2. So, which is just a composition. Okay. So, this is the meaning of this group is acting on this set capital X. Okay. So, the group law also should be preserved. Okay. So, various textbooks actually gives various definition. Personally, I like this definition. Okay. So, let me give you the definition. So, the definition of a group action. So, let us start with G being a group, X being a non-empty set. Okay. So, then we want to say that each element of a group is acting on X. Okay. So, that means because it is actually coming from the group. Okay. So, it should be naturally mapped to some map on X to X, which must be invertible. Okay. That is because somewhat group law should be preserved with that association. So, if you think about this G goes to Tg, if it is a group homomorphism, that is what we are demanding here, that will tell you immediately this Tg must be a invertible map. Okay. So, that is why we demand this definition. So, we say G is acting on this capital X via let us say some map via tau if tau is a group homomorphism from G to Sx. Okay. So, in this situation we say that this G is acting on this capital X. Okay. Each element of the group defines a function from X to X, which is a bijective function. So, recall what is Sx? Sx is nothing but the set of all bijective function from X to X. Okay. So, let us recall the definition. Okay. So, G acting on X via this tau. So, then you have tau is a map from G to Sx. So, where recall Sx is nothing but those maps F from X to X such that F is a bijective map. Okay. This is set of all bijective maps, and Sx is a group with respect to the composition. Okay. Given X to X F and then x to x g, one can talk about F composition G. Okay. So, with respect to that, we have multiplication. The composition of maps gives you the multiplication among x, among these bijective maps. So, this is your group law. Okay. So, that means what? That means, so whenever you actually look at, so maybe I would have had the different thing. So, the multiplication, so let us say is actually given by F star G, this is the multiplication, I simply take the composition. Okay. So, both are make sense. So, this is G, this is F. So, this is your group multiplication in Sx. Okay. So, let us unravel all the things that are encoded in this one definition. So, this is just being group homomorphism. Okay. So, what is the meaning of that? Let us rewrite things. Okay. So, given each element G in capital G, we have this tau G, which is a map from x to x. So, this is a bijective map. Okay. So, first of all, so that is the first thing, it is a map, tau is a map from G to Sx. So, that means given each element you have this tau G. So, now if you think about it, the tau identity, okay, because tau is being a group homomorphism, tau identity must be identity function on x, because identity function on capital X is the identity element in Sx. Okay. So, 1 x of small x is defined to be x for all x in capital X. Okay. So, now if you take any tau of G inverse, okay, tau G inverse, which is tau of G inverse. So, from the group homomorphism property, we know that the inverse of an element is mapped to the inverse of the mapped element. So, that means, so this is tau of G inverse, so which is exactly tau G inverse inside your Sx. The inverse map associated with tau G is what image of tau G inverse, and these are all like immediate from the group homomorphism. And the definition of group homomorphism tells, if you take G1 G2, tau of G1 G2, then that must be the composition tau G1 tau G2 inside Sx. Okay. So, this is just possessed in this information inside tau being a homomorphism from G to Sx. Okay. So, in that case we say that G is acting on this capital X via this tau. Okay. So, if you think about it, what we are indeed doing. Okay. So, you have this set capital X, okay, and then you have this group G, and then you pick some element G in capital G. So, then this tau G gives you map from capital X to capital X. It is a bijective map. We can also call it a permutation. Okay. So, tau G is a permutation of capital X. So, then what this does, if you take some small x, okay, so this small x is mapped to tau G of x under this tau G. So, this is just simply each element of the group is just simply permuting all the elements of capital X. And of course, group has this group law, okay, the compositions are there or the product is there on the groups. That product should actually obey when you take the compositions. Okay. The tau G1 G2 should be same as tau G1 composition tau G2. Okay. Because of this, you can see that tau identity should be the identity element of x and tau G inverse should be tau G of inverse. Okay, all these things should be satisfied. So, in some books, so these details will be written in detail and then they call that as actually group action. Okay. Let us see that definition as well. Okay. I will leave it to you to verify those two definitions actually are equivalent. So, this is our first definition. Okay. Let us call this as a first definition of group acting on x via tau. Okay. So, here is the second definition. So, the second definition again motivated from the first definition. Okay. So, if you think about it, so given element G and given element in capital X, okay. So, you can associate one element in capital X. So, you take some G and then you take some X and then you can send this to tau G of X, okay, if tau is there. So, that means you can think group action as a map from G cross X to X satisfying some properties. So, let us write down what it is. Okay. So, when you say G acts on X, let us say via now some pi, where pi is a map from G cross X to X, which is given by G comma X goes to pi of G comma X. Okay. We say this, we say G acts on X via pi if the following satisfied. If the following conditions are satisfied. Okay. So, what are all the conditions? So, those conditions can be worked out using the original first definition, definition 1. Okay. For example, let's see what happens if you take identity and then X. So, where it should be mapped? It should be mapped to tau identity of X, tau identity of X, but that is exactly 1 X of X, which is just X. So, that means, so that I can put it as a first definition, pi of identity X is X for all X in capital X. Okay. So, then the second condition, when you take the group law G1 G2 map to G1 G2 of X. So, that is mapped to tau G1 G2 of X, okay. But what it is exactly? It is exactly equal to tau G1 composition tau G2 of X, okay. So, that is exactly the composition. So, which is tau G1 of tau G2 of X, okay. So, this is what it says. So, this is something we want to rewrite in terms of this pi. So, let us see how we can write this pi of, now you take G1 G2 comma X. So, this should be what? First you apply pi of G2 comma X. So, that is tau G2 of X. This is an element in capital X, okay. So, then you apply pi of G1 on this, okay, that is what it says. So, pi of G1 comma pi of G2 comma X. So, this is first element in capital X and then you apply G1 again, okay. So, these two properties should be satisfied. So, from this you can see that, so the corresponding map, okay, G goes to tau G. So, now what will be the tau? Okay, given now pi, so we can define tau as follows from G to Sx. So, how one can define this? So, this is tau of G to be just pi G comma dash. What is the meaning of that? That means if you take, okay, this is our tau g, sorry, this is our tau g. So, tau g of x you define to be pi of g comma x. Okay. So, you can also add this another condition like pi of g inverse comma x. So, that is going to be, okay. So, that is tau g inverse. So, tau g inverse of x. Okay. So, maybe that is inbuilt already in this. So, we do not need to worry about it. Okay. To verify these things, okay. So, given pi, so given pi, we can define this tau as follows. So, then we need to verify that. So, definition 2 implies definition 1. For that purpose, we need to verify tau is indeed a group homomorphism. Okay. So, let us check. So, what we are verifying? We are verifying now definition 2 implies definition 1. Okay. So, from given pi, you define this tau, which is a map from G to Sx. Okay. So, to say that it is a map from indeed G to Sx, we need to verify this pi G dash, which is a map from x to x, is indeed a bijection. Okay. So, if you can verify this, then you are in good shape. So, let us try to verify this. Okay. So, what happens when you take pi g comma dash from x to x? So, this is going to map x to pi g comma x. So, now what is given? Given is the pi is given. So, g is acting on x via this pi, where pi is a map from g cross capital X to x, satisfying these conditions. Okay. Only these two conditions. So, from this we want to say that the map that we define tau, which maps g to, okay, this tau g, which is pi of g comma dash, that is actually a group action using the first definition. For that purpose, first we need to verify this x goes to pi g of x is a bijective map. So, it is a map that is very clear. Why it is bijective? So, if you think about it, so pi g inverse comma x is going to be pi g comma pi g inverse comma x. Okay. But pi g inverse x is nothing but pi of E identity x, which is just 1 x of x, which is x. Okay. So, that tells us that pi g comma pi g inverse comma x is nothing but x. Okay. So, given x, you can take y to be this pi g inverse comma x. So, that is your inverse image. Okay. So, given x in capital X, take y to be pi g inverse comma x. So, then it is clear that pi g comma y is x. Okay. That proves that pi g comma dash is indeed surjective. Okay. So, this proves that pi g comma dash is a surjective map. Why it is injective? So, it is injective again from the same reason. Okay. Let us say you have two images are equal, pi of g comma x 1 equal to pi of g comma x 2. Okay. So, now if you plug in this inside pi of g inverse of g comma x 1. So, using the well definers of pi, you get this is same as pi of g inverse of pi of g comma x 2. But what it is? So, if you go back to the original definition, so pi of, if you take g 1 here, g 2 here, then it has to be the composition. Okay, that is the definition. So, if you go back to the definition, so here it is, whenever you take G1 here, G2 here, you have to compose here G1, G2. So, that tells us that okay, this pi of this side, left hand side, is G1 inverse G comma x1. Similarly, this is pi of G inverse G comma x2. But what is this? This is pi of E x1, which is x1, and this is pi of E x2, which is x2. So, that proves that x1 equal to x2. Okay. So, this is what we wanted to prove. If you take the images are equal, pi of g comma x1 is same as pi of g x2, then we want to prove the pre-images are equal. So, that proves pi is injective. We already proved pi is surjective, and here now we proved pi is injective. So, that proves that pi of x g comma dash is pi of g comma dash is surjective map, bijective map. So, that means the tau that we defined using pi. So, let me call it okay, maybe tau upper pi, which is a map from G to Sx given by tau pi of G is just pi of G comma dash. Okay. It is a well defined map. Okay. Now, I will leave it to you to check. Okay. This is something you can check directly from again the definition, that this tau pi is indeed a group homomorphism. So, that means tau pi of G1 G2 should be same as tau pi of G1 composition tau pi of G2, and again that will come from the definition of pi. Okay. So, that means from definition 2 one can get definition 1, and I will leave it to you to check again from definition 1 you can get the definition 2 by defining pi to be this. So, this is the pi tau, let us say. So, given tau, you define this pi tau to be g x goes to tau g of x, then that will define you actually the group action that is listed here. Okay. So, many books actually gives this pi definition, the second definition for the group action. Okay. But indeed I would recommend you to remember this definition. This is somewhat more natural definition. So, each element of the group is acting as a bijective map on capital X, and of course, that association G goes to tau G should preserve the group loss. Okay. So, then you say that this group is acting on capital X. So, because we are not having any other structure, we want to talk about group action in more abstract way. So, that is why we are demanding only the G goes to tau G, where tau G is being just a set theoretic bijective map. Okay. Of course, when you depending upon, so what you do if you are in topology, geometry and so on. So, you demand more on this association. For example, you can take in topology that tau G are all being continuous maps or homeomorphisms and so on. Okay. Or if you are in linear algebra, you can demand it to be all linear invertible maps. But anyway, so such situations can arise later, but here in the more abstract way, we just say that group G is acting on X if there exists a group homomorphism tau from G to Sx. Of course, if you want to say just G is acting on X, so then we can hide this tau. We can simply say that there exists tau such like this. Okay. So, in practice what we do, we do not indeed use this tau often. Okay. Again we will use this shorthand notation. So, what is this shorthand notation? We suppress this tau. Okay. We say that there is this action from G to action of G on X. Then instead of writing, so given X in X, So, the image of tau g of x, okay, that is sometimes written as g dot x. Okay. So, this is the shorthand notation. So, this is very often used, okay, but this should not be confused with group multiplication. So, warning, okay, this g dot x should not be confused with group multiplication, because there is no group multiplication, because this x is coming from capital X and g is coming from capital G. Okay. They are two different sets, okay. But we are looking at the corresponding map tau g which is acting on capital X. So, we are looking at the image of x under this tau g, which we just denoted by g dot x. Okay. So, I will stop here and then we will continue with group action in the next class. Thank you.